today. So we're going to pick up where we left off yesterday, which was with translating words into math symbols. And we went over some of the basics. We went over phrases that meant addition and translating them into addition. And we went over subtraction. And the same things happen for multiplication and division. Some of the words that we saw, there were keywords for addition. We saw increased by, and we saw plus, greater than, saw the word sum, which is the result of an addition problem. Some that we maybe didn't hear or didn't see were added to. For subtraction, we saw decreased by, less than, minus, the big term difference. A difference is the result of a subtraction problem. Taken away from, or take away, and different derivations of those phrases. So I want to pick up today with this one. A number repeated 7 times. And I'm going to ask you to use n for our unknown number. So how would we express that using numbers and symbols? First of all, what operation? Multiplication, okay? A number repeated 7 times is just 7 times that number, or a number times 7. You could actually have done repeated 7 times. Let's see, one more, it looks like. Could have added it together 7 times, but we know repeated addition is actually the definition of multiplication. Now, when we have a number and a symbol like this, we don't have to put the multiplication symbol in there. We can just write it as 7n, and that's typically the way you'd see it expressed. So some other phrases that would be represented by the symbols 7n. What can you think of? I'll give you the easy one, very similar to the one I gave you up there, just 7 times a number. Any others you can come up with? For addition, we had the sum. For subtraction, we had the difference. Does anybody know the equivalent word for the name for the result of a multiplication product? Seven of a number. That can work. I actually just let the one slip. The product of a number and 7, or 7 and a number. That product is the result of a multiplication problem. Some of them are so easy as you don't even think of them. A number multiplied by 7. And again, there are a number of other possibilities we could come up with. that would describe 7n, or 7 times n. Let's move on to a number split 4 ways. And I'm going to ask you to use t for our missing number. So how would we express a number split 4 ways? T over 4 or t divided by 4? Perfect. Both of those are perfect. Typically, just for compactness, we use t over 4. But both of those mean the exact same thing. So what are some other phrases that would be translated into t over 4 or t divided by 4? A number divided by 4, perfect. Others? Now, if you remember doing the goes intos when you were in elementary school, and 4 goes into a number. What's the fancy word for division? Like we had the sum, the difference, the product. There you go. The quotient of a number in 4. And of course, if we thought on it, we could probably come up with several other ways of expressing t divided by 4, or phrases that would be translated into t divided by 4. The real trick, the real difficult part comes when you start combining operations into a single phrase and trying to then write those out. So we might have 7 less than 5 times a number. I'm going to ask you to use D for our missing number. Perfect. 5D minus 7. And as we decode that, 7 less than means 7's being subtracted from something. So we start out with the minus 7. And what is it being subtracted from? 5 times a number is the 5D. Perfect. We might have the product of a number and 5 reduced by 7. How's that going to look? It's going to be exactly the same. The product of a number and 5, that's 5D, reduced by 7, minus 7. How about 5 times the difference of a number and 7? What's this one going to look like? Okay, 5 times, what's that? There we go. X minus 7 or D minus 7. Why does it have to be in parentheses? Okay, because this phrase is telling us that the subtraction happens first. So we have to put parentheses around it. Otherwise, we discussed order of operations. Otherwise, order of operations would do the multiplication first. How do we know that the subtraction is done first here? Well, if we look at the others, let's go ahead.
It says difference.
Yeah, the difference. It's 5 times the difference. The difference is the result of a subtraction. Up here it was the product of a number and 5 is saying 5 times the number, 5 times the number. In both of these first ones, it's the number that's being multiplied by 5. Down here, it's the difference, 5 times the difference that's being multiplied. So that means we have to do that difference of the number and 7, d minus 7, first, and then multiply it by 5. So those things come up all the time, and they can be tricky. Another one that's pretty tricky to distinguish between is this one. Eight is less than a number. 8 less than a number. Let's start with the first one. Anybody tell me what that would look like in symbols? Okay, if we use X, it wouldn't be an equals, though. It would simply be the less than symbol. Oh, sure. And in a lot of cases, is does mean the equal symbol. But here it's is less than combines to make that phrase. And that's the huge difference. Is less than compared to just less than. How do we express that second one? Eight less than a number. If there we go, 8 minus or X minus 8. How many of you have problems remembering which direction, which symbol is less than and which one's greater than? Anybody? A little bit? Okay. Where those symbols come from. 8 is less than X. What that's saying is we have 8 somewhere and we have X somewhere on our number line. 8 is less than X is saying 8 is on this side of X. So the less than symbol actually comes from the arrowhead on the left end of the number line. That is the smaller end of the number line. So 8 is on this end of the number line compared to X. If we were comparing 9 and 2, well, 9, here's 9, here's 2. 9 is on this end of the number line compared to the 2. If that makes any sense. Hopefully that helps you remember. That's actually where those symbols originated from. So let's try something like um, 3 less than 5 times the sum of a number and 8. There's a lot going on here. We just take it from the beginning, we can decode it. I'm going to give you a second to look at it, possibly write down what you think it's going to be, then we'll talk about it. Okay, so as we start from the beginning, 3 less than something, what does that mean? We're subtracting 3 from something. Good. Now our next phrase, 5 times, says something's going to be multiplied by 5, but what's going to be multiplied by 5? 5 times the sum. So that tells us yes. Is the x plus 8 first. What do we have to do with that x plus 8? Parentheses, good, because we need to multiply by 5, good. So this is 3 less than 5 times the sum of 8x plus 8, or number 8. So let's add in the next step. Four times the number reduced by 7 is 29. So as we look at that, now this is where you said you saw that word is before, and in this case it does mean that. What does is mean? Equals, good. So what's on one side of it has the same value as what's on the other side. So let's look at what's before the is, or before the equals. 4 times a number reduced by 7. How do we write that? 4x minus 7. Very good. Then the other side is simply 29. Good. Now there are other phrases other than just the word is that simplify the equal sign. Some are a little bit more complex than that, but they all mean the equal sign. We might have 5 more than a number squared is the same as 7 times the number reduced by 5. So a lot of times in these problems, it helps to identify, just like we did in this first example up here, to identify where the equal sign is. In this phrase here, what set of words, what phrase stands for the equal sign? Is the same as. So that's our equal sign. So then this part before it is going to go on one side of the equation. 5 more than a number squared. But of course, 5 more than means adding 5 to something. A number squared? N squared, x squared, whatever we're going to use, yes. N squared we'll use. Again, in my math lab, you got to watch for the letter it tells you to use. So now the other side, after that phrase, is the other side of the equation. 7 times a number reduced by 5. How are we going to express that? We used n over here, so we got to make sure we use it over here. But yeah, sure. And that's one of the reasons why I try to throw in other letters, because x seems to be ingrained in us. Whenever you think of a missing number, it's always x. So yeah, 7n minus 5. Now, solving equations like that we'll get to at some point. For right now, we just want to get the phrase written down. Okay, so we talked last class, yesterday, about order of operations. And that order of operations has come into play in a lot of places so far. We saw it just for evaluating, expressions or calculating multiple operation problems. Things like 7 plus 2 times 8 squared minus 3. Things like that. So the order of operations told us what to do. We also used it for evaluating. We might be given, evaluate 2m minus c plus d over 3x for m equals 11, c equals 9, d equals 12, and x equals 1. So we had to substitute those values in for the variables, in for the letters, and then follow the order of operations. And then we saw today even when we're writing expressions, when we're translating, that order of operations comes into play when we did things like 6 times the sum of a number and 2. Because we know that order of operations says we multiply before we add, if we want to do the addition first, the sum of a number and 2 had to come first. We used parentheses to signify that we did the x plus 2 first and then times the 6. And that order of operations comes into play in all sorts of different places as we go through our concepts in math. It is one of our basic concepts. If we go back to day 1 last week, we talked about the operations of addition and multiplication in those rules. Those 2 basic rules follow through in all of the different types of numbers we're going to work with. Well, this idea of order of operations follows through as well. In fact, let's take a peek at some more things dealing with that idea of addition and multiplication in those rules. We saw the place values came into play when we did our basic operations. Our basic place values, if we start at the decimal point and work our way to the left, we have the ones. What's next? Tens and hundreds. And those are actually our only 3 place values. They get repeated over and over. Ones, tens, and hundreds. Ones, tens, and hundreds again. Well, this first set here is our base group. The second set, we know, is our thousands group and our millions group. We go into the billions and trillions and so on. We've talked about exponents. Having those 2 parts, having x to the 4, having a base, and then having the power. Well, our number system is referred to as a base 10 number system. What that means is our place values actually come from exponents with a base of 10. Most of you probably recognize 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 is the 1,000. 10 to the power of 4 is the 10,000s. 10 to the power of 5 is the 100,000s. 10 to the 6 is the 1 millions, and so on. Math is about patterns. You might see me throughout the semester do some rather long calculations in my head, and what it comes down to is patterns. In fact, in math, there's a lot of times we can't do something with our basic definitions, so we define the result to be whatever continues a pattern. And here's kind of an example of that. We see 10 to the 6th, 10 to the 5th, 10 to the 4th, 10 to the 3rd, 10 to the 2nd, 10 to the 0. What do you think this one has to be to continue that pattern? 10 to the 0, right? 2, 1, 0. 10 to the power of 0 equals 1. It's our ones place. If we were to keep going on the other side of the decimal point, what do you think this next one has to be here? That would be 10 to the negative 1. We go 3, 2, 1, 0. It has to be negative 1, negative 2, negative 3, negative 4. Well, what's the name of this place value here? What do we call that? It is the tenths. So 10 to the negative 1 is 1/10. This one is the hundredths. So 1/100th or hundredths is 10 to the negative 2, and that continues. As we saw last week, those place values play an important part in our operations. We might have 436 plus 252. And we talked about how you can only add things with the same name. $436 is really 4 hundredths, 3 tens, and 6 ones. 252 is really 2 hundredths, and 5 tens, and 2 ones. And since we can only add things that have the same name, it comes right down to the place values, the digits. Each individual digit has a count and a name. I can only combine 3 tens with other tens, the hundreds with other hundreds. That's why it's been stressed to us to line up those columns when we add and subtract. Once they're lined up, we can just go ahead and add. 400s and 200s make 600s. 3 tens and 5 tens make 8 tens. 6 ones and 2 ones make 8 ones, 688. Now, when I did that, you may have noticed I did something a little strange. What did I do that's different than usual? Yeah, I went left to right. Normally, we go the other direction. Why do we usually go right to left? In case we have to carry. We have things like 700 or 578 plus 294. We start on the right and go back to the left because we can run into this. What's 8 plus 4? 12. So we've been taught you keep the 2 and carry the 1. 1, 7, and 9 is 17. So we've been taught to keep the 7, carry the 1. 1, 5, and 2? 8. And that's the way pretty much all of us have been taught to do that. Believe it or not, one of the myths that gets commonly put out there in math is that there's only one correct way to do things. There's only one correct answer, but there are several correct ways of doing things. Right now, carrying is the popular way to add. Before my time, but about 130, 140 years ago, a popular way to add would have looked like this. We would have started on the right or on the left and worked our way to the right. 5 plus 2 is 7. 7 plus 9 is 16, so 6, drop the 1. 8 plus 4 is 12, so 2, drop the 1. 872. The reason I'm showing you this is not to confuse you, not to try to change the way you add. I just want you to see that there is more than just one way to do things mathematically. There's only one right answer. Both of those methods give me the exact same answer, but there can be more than one way. Throughout the semester, especially when we talk about operations with algebraic numbers in the next couple days, you're going to see a lot of things that are different than what you've seen before. That doesn't mean you can't still do them the way you've done them before. It just means there's alternatives. We saw the same thing with multiplication as far as being able to combine the different place values. One thing I want to show you before we move on is division. Where does our process of long division come from? This is one that shocked me when I saw the full process, because what we've been taught is such an extreme abbreviation, a shortcut of the process. So it doesn't look anything like the real process. Remember we discussed that multiplication and division are the same operation. One goes forward, one goes reverse. So they follow the same rules. If we look back to when we first started to multiply, like 5 times 3, before we memorized our multiplication tables, and before we knew that 5 times 3 was 15, how would we figure that out? If I remember doing this, 5 plus 5 plus 5, we turned it into repeated addition. If multiplication is repeated addition, division can be turned into repeated subtraction. 24 divided by 8 means I'm going to subtract 8 from 24. 24 minus 8, that's 16. I subtracted it once. Minus another 8 is 8. We subtracted it twice. Minus another 8, of course, is 0. We subtracted it 3 times. 24 divided by 8 is 3, because we can subtract 8 from 24 3 times. So to a more complex example, what if we had 97, let's make it a little simpler than that. Let's go with 96 divided by 4. I don't want to start subtracting 4 from 96. But what I can do is I can start subtracting large bundles of 4. And what I mean by large bundles, I use those place values. Let's try tens. What is 4 times 10? It's 40. Can I subtract 40 from 96? Of course I can. In fact, I can subtract it twice. 2 times 40 is 80. If I subtract 80, what do I have left? 16. Well, that 80 represents bundles of 4 that I have subtracted. 10 4s made 40. I did that twice. So 10 times 2 is 20. What that 80 represented was 24s. I subtracted 4 20 times. That's where the 80 came from. Now out of the 16, I could subtract 4 more times to get to 0. So I subtracted it 20 times. I subtract it 4 more times. That's a total of 24 times. So 96 divided by 4 is 24 because I can subtract 4 from 96 24 times. This is exactly the process of long division that we were taught. Let's just take 75,283. And I'm going to divide by, let's go 21. Now this could get pretty ugly, but let's see what happens. Now again, I'm not about to start subtracting 21 from 75,000. I just don't have that kind of free time. But we can subtract a large bundle of 21s. How do I know how big of a bundle? I look at my place values of the number being divided. What's the place value of that 7? 10,000. Good. What is 10,000 times 21? Plus 210,000. Can I subtract that from 75,000? No, it's too big. So we moved on to the next place value, which is 1,000. 1,000 times 21 is 21,000. Can I subtract that? Yeah, in fact, I can subtract it 3 times. 21,000 times 3 is 63,000. So I've got 3, 8, 2, 2, and 1. 12,283. How many times what did I just subtract here? How many bundles of 21? Yeah, 1,000 times 3. I just subtracted 21 3,000 times. My next place value is the hundreds. 100 times 21 is 2,100. Can I subtract that from what's left? Yeah, in fact, 6 won't quite go, but I can subtract it 5 times. 2,100 times 5 is 10,500. I subtract, that's 3, 8, so 1 and a 12, 1,783. How many 21s did I just subtract? 500. Good. 100 times 5 is 500 more. My next place value is 10. 10 times 21 is 210. Can I subtract that from what's left? You bet. How many times? Let's try 8. 210 times 8 is 1,680. So that works. We've got 103 left. How many times did I subtract 21 there? 80. Very good. 80 more times. Now the last place value, all that I have left, is 1s. 1 times 21 is 21. Can I subtract that from what's left? Sure. 4 times. It'd be 84. Leaves me with 19. So that is simply 1 times 4, or just 4 more times. If I wanted to keep going, my next place value here, yeah, is the 10th, 0.01. That's 2.1. And I can subtract that from what's left. We don't want to get into the decimals for right now. We could leave that as just a remainder of 19 if we wanted to. So this goes in there, 3,584 with a remainder of 19. Now you're probably looking at that thinking that looks absolutely nothing like what I was taught for long division. But it's actually exactly what you were taught. Most of us were taught to do this. Does 21 go into 7? No, so we leave that blank above the 7. That's exactly what we did here. 10,000 times 21 is 210,000. It's too big. We move to the next place value. Here's our next place value. Does 21 go into 75? 3 times. 3 times 21 is 63. If we look closely here, that's exactly what we did. We just left out those zeros. So we subtracted that 63. We got 12 here. Some were taught just to bring down the next number. Others were taught to bring everything down and keep track of where you're at. It works out the same. 21 goes into there 5 times. 5 times 21 is 105. Again, you see, it's exactly what we did here. We just left out all those zeros. So what we've been taught is just a severe abbreviation or shortcut of the real longer processes. One of the reasons I bring this up right now is in the next couple of classes, we're going to get into operations with algebraic numbers. And as we do that, we're going to see these same rules, these exact same rules apply to algebraic numbers. It's just, it looks different because we never saw what really happens with our whole numbers. So anyway, as we look at algebraic numbers, we see things like 5x squared plus 3x plus 9. I mean, that doesn't look anything like other numbers. In fact, most people look at that and they think they see 3 separate numbers. It's not. That's a single number with 3 digits. Think back to a number like 824. When we wrote that in our expanded form, it was 8 hundreds and 2 tens and 4 ones. But as we saw a few minutes ago, one of the other ways we can express ones, tens, and hundreds is just using power of tens. This could be, this could be 8 hundreds is just 10 squared. 2 tens is just 10 to the 1 or just 10. Plus 4 ones would be 10 to the 0, but often we just write 4, and the ones is implied. If we look at this and compare it to that, sorry, I'm losing my voice again. As we compare those two, you start to see similarities. Instead of the 10 squared digit, that's the x squared digit. Instead of the tens digit, that's the x digit. This is the 10 to the 0, which is 10 to the power of 0 is 1. This is the x to the power of 0, which is 1. Anything to the power of 0 is 1. So it doesn't matter what we're using as the base of our place value. That last digit's always the ones. So when you see them compared this way, what you see is our algebraic numbers are just the same as our whole numbers with a different number base. So as we start to do some of those operations with them, we should see that they follow the exact same rules as whole numbers. If I were going to take that 5x squared plus 3x plus 9, now I'm going to put it in parentheses. In this case, the parentheses are not an enclosing symbol. All they're doing is telling us that that is a separate number. So not all parentheses are enclosing symbols. Sometimes they're just a separator. Plus 2x squared plus 8x plus 7. We've all been taught strategies for adding them. The most common strategy is when you add the name for algebraic numbers, polynomials. Typically what we've been taught to do is remove the parentheses and just combine like terms. 5x squared and 2x squared make 7x squared. 3x and 8x make 11x. 9 and 7 make 16. And again, that's a great shortcut. It saves a lot of time. But what's really going on there? We have 5x squared plus 3x plus 9 plus, I'll put it off to the side here a little more, 2x squared plus 8x plus 7. We've lined up the x squareds with the other x squareds, the x's with the other x's, the ones with the other ones, because when we add or subtract, we only combine things with the same place value, just like lining up the columns with our whole numbers. And now it doesn't matter whether we start on the right or the left. We'll start on the right and work our way backwards just because that's what we're used to. 9 plus 7 is 16. It's a positive 16, so we put a plus in front of it to connect it with the other numbers. 3x plus 8x is 11x. 5x squared and 2x squared is 7x squared. So you can see there the process, it's really the same base process as adding whole numbers. We've just come up with shortcuts or abbreviations to make it a little quicker. One of the big differences there's actually a couple of big differences between our whole numbers and these algebraic numbers. One is, of course, the algebraic numbers always have to be written out in an expanded form. We have to have the place values written in there. We can't write it just 287 and imply that that's 2x squared and 8x plus 7. For a couple of reasons. One is we don't know whether it's an x or a y or what that place value is. The other is we see here that it's not just one digit in a place value. We're not limited to 0 through 9. We can have 11x or 25x or even 16 ones and so on. So we have to write them out in that expanded form. The other big difference between our whole numbers, or actually our integers, and the algebraic numbers is our negatives. With an integer, either every digit is positive or every digit is negative. What do I mean by that? Well, if we have negative 239, that's a negative 200s and a negative 3 10s and a negative 9 1s. Every digit is negative. However, in an algebraic number, it's possible to have 5x squared, a negative 3x, and a positive 12. Each digit in an algebraic number can be positive or negative on its own. That adds a different level of difficulty to us. We'll spend more time tomorrow looking at these operations with algebraic numbers, but I wanted to tie them together today just so that you saw that connection between the place values of whole numbers and integers and the structure of a polynomial, the place values basically of an algebraic number. Our last thing that we want to look at today, and probably get done just a little bit early today even, is going back to evaluating expressions. Only now we're going to be evaluating expressions to test equations. What do I mean by that? Well, if I give you 3x plus 11 equals 5x minus 3, and I tell you a possible solution is x equals 4. How can we tell if that's the solution? Well, we can simply replace x everywhere it appears in this equation with 4. So the left side of this equation is going to become, instead of 3x plus 11, it'll be 3 times 4 plus 11. The right side of the equation, instead of 5x minus 3, is going to become 5 times 4 minus 3. And then we do our order of operations on each side separately. On the left side here, what do we have to do first? 3 times 4 gives us 12. Good. What's next? 12 plus 11, which is 23. That's all we have to do on that side. On the right side, what do we have to do first? 5 times 4 is 20, so we replace the 5 times 4 with 20, and then subtract the 3 to get 17. That is obviously not true. For that to work, we have to have the exact same value on both sides. So that's telling us x equals 7 is, or x equals 4 is not a solution. So the next solution I want you to test is x equals 7. Still using the same equation. 3x plus 11 equals 5x minus 3. What's the left side going to become as we substitute in 7? 3 times 7 plus 11. Good. If we do our order of operations there, what are we going to get? Perfect. 21 plus 11 is 32. Good. On the right side, if we substitute in the 11, what does that expression become? Or sorry, 7, I should say. 5 times 7 minus 3. As we evaluate that, what does it evaluate to? $35 minus 3, which is 32. So we have the same value on each side, which tells us that's true. So we have a solution. X equals 7 is a solution to that equation. It makes it true. It gives us the exact same value on each side of the equal sign. Some things that we've seen, we've mentioned and talked about, but I want to make sure we just put it out there in words so that everybody has it. I'm going to use numbers as symbols. It's easier that way. 5 plus 2 and 2 plus 5. Are they equivalent? Yes, they are. 7 times 3 3 and 3 times 7. Are those equivalent? Yes. Those are what we call commutative. Commutative means we can switch the order of the numbers in an operation. Those are what we call base operations. Addition and multiplication are referred to as base operations. Along with those base operations, we have something called inverse operations. Every base operation has an inverse operation. What is the inverse operation to addition? Subtraction. Without addition, subtraction has no definition. Subtraction is actually defined to be the reverse or the inverse of addition. What is the inverse operation for multiplication? Division. Our properties of numbers, the one that we saw here being commutative, oops, go back here. Our properties of numbers only apply to our base operations. They do not apply to those inverse operations. If we're dealing with more than two numbers, we might have 5 plus 7 plus 2. All of our mathematical operations are what we call binary operations, which means you can only use two numbers at this given time. You can't do three numbers at once. So when we look at this, you do the 5 plus 7 first, and then you add the 2. However, some people might find it easier to do the 7 plus 2 first, and then add the 5. Are those equivalent? Yes, they are. Both of them give us 14. We might have 3 times 5 times 6. And again, many would do the 3 times 5 first to get 15, and then multiply by the 6. But would it be equivalent to do the 5 times 6 first and then multiply by 3? Yeah. Either way, we're going to get 90 as our result. That is what is referred to as the associative property. When combining 3 or more numbers, we can pick any two of them first, as long as it's multiplication or addition. Again, it only applies to those base operations, not the inverse operations. Notice that they are all either all addition or all multiplication. You can't mix operations in the associative property either. Each of our base operations have something we call identity elements. Identity means you get the same thing, they're identical. For addition, if I have the number 5, what can I add to it that keeps it a 5? 0, very good. 0 is the identity element for addition. If I start out with the number 7, what can I multiply that by to keep it a 7? 1, perfect. 1 is the identity element for multiplication. Now, the reason those are important is when we go to do inverses or to invert them, we want to get back to the identity element. The inverse of a number gives us the identity. So if I have a 5, the additive inverse, what I can add to 5 to give me the identity of 0 is -5. Very good. If I have 7, what I can multiply 7 by, now the identity element for multiplication is 1, so I want to turn it into a 1. What I can multiply 7 by to give me a 1 is 1/7. So for addition, so my negative disappeared here. The inverse of a number for addition is just the opposite or the negative of that number. For multiplication, the inverse, anybody remember the term we use for that? It's called the reciprocal of that number. Okay, that is enough for today. That is our properties and everything. Remember now there is homework. 1B out there, that is listed as being due tomorrow. Again, its final due date is January 28th. I just highly recommend that you do it before tomorrow so you don't have them stacking up on you. The quiz 1 is out there, but I'll warn you, when you start a quiz, you have to finish it. If you'll try to log out of the quiz, actually, I guess I do have it set, so you should be able to log back in once, and it won't cut you off. But you don't want to be going in and out of a quiz, or it'll cut you off. So the quiz, I would wait until after our class tomorrow so that you've seen all the material before you do it. But quiz 1 will be due on January 28th. So next Monday is when we wrap up all of this week's material. Those quizzes in my math lab will only let you do them two times, 2 attempts. Of course, the homework, you can do it as many times as you want to till you get it right. Oops, go ahead. Even after you click OK and submit it, you can go back and redo the homework more times. The homework really is graded for completeness. As long as you attempted every problem, and if I go in there and I see that you got a 0 on a bunch of problems, I can actually go in and see the time spent. And if I see that you had 1.8 seconds on a problem, that tells me you were in a hurry, threw down an answer, and moved on. So as long as you're putting in the time on the homework, you get those points for it. It's the quizzes that you're graded for the accuracy. Any other questions? Okay, I think we'll call her a day then. We'll see you all tomorrow. Have a great day. Hopefully my voice gets stronger here as the semester goes on.